Very good hustle, Dylan. All right. Would you want to change seats today? I know that Michael and Britton are not with us. Let's see. I know, creatures of habit. I like to sit in my seat, even if given the opportunity. But we do have the opportunity closer if you would like. If there's any takers throughout today. I invested probably 4.5 hours in our exams yesterday. I definitely thought I would get. I ran out. I'm so sorry. We will definitely get them back tomorrow. Definitely. So if you don't mind being patient, they are exceptional. Your justifications were spot on. We're spot on. Oh my gosh, so good. But we'll get them back tomorrow. So today, want to start with some warm-up questions to get us in the thinking of bonding. Make sure that we understand that whenever we read lattice energy or we're given ionic compounds or question about ionic bonding, we relate these two things. So when we think of gases, ideal gas law, STP, there's certain things to bring to mind. Well, lattice energy, we only speak of that with ionic compounds. Ionic compounds, we're usually going to be asked about lattice energy. And then we'll practice a couple of those questions. Then the meat of today. Hooray! Lewis dot structures for covalent. We'll see things that obey and that do not obey and why the octet. You may have heard of resonance before. Oh, formal charge. Such neato stuff. So that will be today. Questions? I'm so glad you guys are here today. The others are missing out. I saw something very funny. There's an elementary principal that I follow, and he was recording himself saying he was calling parents. Maybe you won't find this. I found it very funny. And he said, parents, just to remind you, there's only 2 days that you're sending your kids to school this week, but we thought we'd give a gift, a Thanksgiving gift. I'm so glad you're here. To parents, even though we have 2 days, we are going to have them be excused absences. Yes, excused absences on Monday and Tuesday. In fact, if we do not see your children, we will outfit your whole family with school. So I guess some parents saw that and thought it applied to them. Now, I know that Michael and Grit weren't going to be, but I definitely. Anyway, Holly, so glad you're here. It's not complete if we're missing any of us. I know we're so excited for Thanksgiving break. One more day. All right, page 7. Page 7. Our warm-up questions will be 1 through 5. Easy peasy. 1 through 5. Let's take 5 minutes. We probably won't even need that. Again, page 7. For sure. electronegativity table a couple of pages prior to that. I included this bottom one. I thought we'll take 30 more seconds. More time. All right. As a class, why don't we go ahead and just answer 1 and 2 together? So the answer to 1 is 1, 2, 3. FON, that is the order. The most electronegative, then oxygen, then nitrogen, then fluorine, bromine. So in that order, if you want to remember that. So oxygen, obviously. And then number 2, the correct answer, 1, 2, 3, B, excellent. Now, covalent bonds. Covalent bonds are being broken. Be careful. Covalent bonds are not being broken during a phase change. Here, nope. In fact, if we wanted to, this is probably metallic, if that. And then here, we're just liquefying. So we would be increasing the kinetic energy to equal particle attraction. We're not breaking bonds. So between A and C, which would it be? Go, Damien. Why not C? Yes. All right. And then 4, A, and 5. So the ranking would come if we're talking about equal sharing of electrons, equal sharing, which pretty much that's only going to happen when you have an element sharing electrons with another atom of that same element. All right, so equal sharing, and then we get toward unequal polar covalent, and then eventually it's so unequal that the non-metal gains, the metal loses, and then we have a full positive and a full negative. Huh? Okay, so looking at these, oh, that is my ionic. So that is going to be the most ionic. I don't even have to check for electronegativity differences. I'm looking at where are they in relationship to each other on the periodic table. So silicon and arsenic, that bond should be the least ionic, the most nonpolar, the most covalent-ish. And then we would have sulfur and bromine, and then carbon and fluorine. Now, if we actually subtract electronegativity differences, if anyone did that, the carbon fluorine is ranked as more ionic. There's a greater electronegativity difference. But metals and nonmetals do not share, do not share, do not share. So based upon composition, it definitely would be the most. Questions there? Yes, Damien.
Less ionic than SBR. Since I thought the BR has 3.45 and S at 3.44. And then
Sure. Okay. The only can I reverse? We're not expected to know any electronegativity values from memorization. We are expected to know the trend, and it is quite handy to know which is the most electronegative, fluorine. And then I would base all my answers from that data. So that's where I'm coming from, just based on location in the periodic table. So we know this is the most electronegative. Okay. And then the closer we get to fluorine, the greater the electronegativity of those elements. And our top dogs, as I just said, fluorine, oxygen, nitrogen, then chlorine, then bromine, and so on. So fluorine, sulfur, I'm so sorry, bromine and sulfur, see, that's on a diagonal. Those are on a diagonal. Diagonals are going to be relatively close in value because of the change in nuclear strength and where the outermost electron is. However, look at proximity to fluorine. So that gave me the assurance, because angle and angle, so then wouldn't we say they're kind of tied? But this is so close to fluorine, that's so close. So I betcha we would expect a greater difference in electronegativity of these two versus these. That's why because we're not expected to know them. We're just expected to rank based upon place on the periodic table. But thank you. And so what was the difference? Oh, yeah. But if we have values, then yeah, but just based upon placement. Yes. Because of proximity to fluorine. Right. So I know what you're saying. So wouldn't these be as equally stronger? Is that what you're saying? I know. Well, if we look at diagonals, see, that's a weird. I guess I chose the one I shouldn't have that here. Don't you know? They're awfully gosh darn close. If we take a look, because Rishi, if we look at other diagonals, oh crud. Well, there's they should be similar. However, they should vary more the closer we get to fluorine. Sulfur and bromine versus silicon and arsenic, because they're closer to fluorine. Okay, so do you see like 3.37, 3.20? Okay. Let's see. 2, 3. What do we think? Go ahead, Maddie.
The numbers are saying that like the silicon percentage of more of it, but the trend isn't. Like, does that make sense?
No, I wouldn't say I know which one to do. Because, I mean, you can find that number on your periodic table on the EID4.
Sure.
And that tells you the electronegativity.
Well, and not everybody is blessed to have your calculator. Right. But I totally get it. Totally get it. Okay. So how do we know? And I know like crunch time on a test. I wouldn't choose two that was a bad choice on my part. So what if we were asked to rank the nitrogen oxygen? How about nitrogen fluorine and carbon fluorine? What if we were asked for those? And then we would just look at where are they on the periodic table? Maddie, we'll get to yours. I promise. And Bryce, I would love to get your thoughts. So carbon and fluorine are separated the greatest of the choices, right? They're 1, 2, 3 apart. These are 2 apart. One apart and then 2 apart. Fluorine is the most electronegative, and then number 2. So I think because they're 4 apart and then fluorine's the most electronegative, this would be the greatest difference. And then I would put nitrogen and fluorine and then nitrogen and oxygen as the most covalent, the least ionic of the choice. Yes.
SNPR is focused on carbon and phosphorus, but they have the same.
Okay. Can we just, using where the elements are on the periodic table, knowing there's exceptions, just based upon where the periodic table is, where they are on the periodic table. So tell me again, which were you speaking of? And carbon and phosphorus. So if we are, see the diagonals, that's where, bleh. So, but I would say, okay, it's a halogen. This is a diagonal. I'm still going to say that this would be the greater difference than this based upon placement on the periodic table. Okay, placement. So the closer we get to fluorine, the higher an electronegativity value. Would we be okay if we were comparing these? So Tyler, does that answer? Very rarely are we ever asked to compare on a diagonal. That was my bad. Maddie, you were talking about, we know there's exceptions to ionization energy, to all the trends, but we just go into it knowing the trend. We get smaller, we get larger. Electronegativity increases, electronegativity decreases. There's bumps in the road, but we're not expected to know any exceptions. Does that address what you were speaking of? Promise, go. I know, I like, this is better. This, yeah. Except for the noble gases. What the heck? We can force noble gases to bond. But as soon as pressure is released, the bonds will dissolve, or whatever you want to say. So no. So that's the only thing. Proximity to fluorine. Promise. I apologize for any confusion. Go ahead. No, I'm so sorry. Whenever I created this was the electronegativity table that I found whenever I was sharing this. And I looked to, oh, those aren't bad. But we know that fluorine is assigned 4 And then all the others are based upon. Okay. We will not use electronegativity values. We make declarations based on where elements are in the periodic table. Is that okay? And how strange, shouldn't an electronegativity value or electronegativity value be consistent no matter what source? No. So, Bryce, is that okay? Are there any other concerns with that? I apologize if there has been. We increase in electronegativity as we move toward fluorine, period. The most electronegative in the order fluorine, then oxygen, then nitrogen. Done. Okay. Hydrogen, way over here, pretty, oh, that's, hydrogen has a fairly low negativity compared to these. We're good knowing that. All right. Any other concerns? All right. Lattice energy. So if you don't mind, I actually have some supplementary pages. So if we find past page 46, the pages read lattice energy 1. Okay. So lattice energy, we just have to associate that with ionic bonding. And ionic bonding, we need to associate with lattice energy. So those two ideas just need to be thought of. Again, you see lattice energy being asked of you. We know it's involving ionic bonding. If a question, this chapter is about ionic bonding, we know it's probably going to involve lattice energy. Isaac, can you remind us, what is lattice energy? That exists. So if we think about a bond forming, is that okay if we kind of like start with that? So choose a metal ion, sir. Sure. So we have the sodium ion, and then it gets close enough, if this is distance between our ion centers, and then potential energy. So choose oxide. Is that okay? All right. So if they're far enough away, they're just doing their own merry thing. But as they get closer, so if we say they're right on top of each other, as they get closer, then the electrostatic attraction is going to start. They are going to start attracting each other. And because we have a positive and a negative, that begins to be released. And so we reach a sweet spot distance when the potential energy is minimized. And so we usually look at it as the energy that's released when they come together, or the energy we have to invest to separate them. So I understand that, sometimes we apply this as force of attraction. So we could say that, the force of attraction, but not the energy holding. Is that okay? All right. So it's the energy released when the attraction is formed, or the ionic bond is formed, or the energy we have to invest to break it. Okay, so if we would go, I'm just going to show us that, there's a lot by the end of today that we will be able to address on our unit assignment. So, Okay, so under ions and ionic compounds, let us see 53. 53. Oh, that is just very bad. It is asking us for the most electronegative. Oh, the most oh my goodness gracious. The most exothermic lattice energy. And we'll go over C is magnesium hydroxide versus magnesium oxide. And let's take a look at A, sodium chloride and potassium chloride. Okay. How do we know? Lattice energy, ionic bonding, lattice energy. Coulomb's law. So we are checking the magnitude of our cation and anion, and then the distance between them. So if we are looking at Mackenzie, in magnesium hydroxide, what is my cation charge? Excellent. Anion charge? Magnesium oxide, +2 -2. If there is a difference in the numerator, that has a greater impact on lattice energy. We don't even have to look at relative size of ions. So Q1, Q2 over distance. My numerator here is +2. My numerator here is 4. So this, because it has oxide versus hydroxide, this will have relatively double the lattice energy. So if there's a difference in our numerator, in the magnitude of charges, but in sodium chloride and potassium chloride, nope. Check charges first. So then I look at D. I have chloride in both. So I'm looking at, this is my chloride. Then the sodium ion in comparison to the potassium ion. Go, sir. Right, the same trend of size. If we're removing an electron from both, we're taking away the highest energy level, but we're doing that with both. So we want smaller. Why? So yep. Oh, and approximately equal to, right? Okay. Okay. Man, another question that is exceptional. 62, and that's an even one. You are told that you're given the lattice energies of FeCl3, so iron 3 chloride, iron 2 chloride, and iron 3 oxide. And the values are negative 2631 kilojoules per mole, negative 5359 kilojoules per mole, negative 14,000, whoa, 774 kilojoules per mole. And you're asked to match which formula would be associated with which lattice energy value. I think we would choose. God bless you. Good. And then, of course, could you justify? That 14,774. And then the smallest value. And then next. Okay. Just have to look at magnitude of charges. Yes, sir.
Like you're looking at the charge of each part.
Yep. What is the charge of iron here? Okay. So if we flip just the page, lattice energy 2. So we watched on Friday Nile Red reacting molten sodium with chlorine gas, and it just produced so much light and heat, it was blinding. What if instead of sodium, we started with cesium, and instead of chlorine, we started with fluorine? So usually, right, we just have reactant and product. Usually that's what we see. But this is in our humanness trying to figure out why do we need all that energy? And then how do we end up getting there? I'm going to number these. And we'll call this 6. Sean, from 1 to 2, what is changing? This would be our start. We're starting with solid cesium. It's a gorgeous, really lustrous metal. And then this is like a palish green gas. So what's the first thing that we're saying on paper probably has to happen? Say again? Excellent. And does that make sense that it's an investment of energy? Solid to gas. Yeah. Then do we see, oh, we're removing an electron. Ionization energies, we have to invest energy to do that. What are we doing, Bryce, from step 3 to step 4? What's changing? Is your cesium ion being changed in any way? No, right? So what is the difference here? F2 and then F. So chemically, what happened from here to there? That required the input of energy. How did you get this bonded fluorine to be individual? Does that require the input of energy? Yes, that would be bond energy. So do we see, oh my gosh, investment of energy? Well, from 4 to 5, we get a little payout. Electron affinity, we're adding an electron, which releases a little bit of energy. But to get our ions separated, to start with neutral elemental cesium, neutral diatomic fluorine, to get them both to be cation and anion, we overall have to invest energy to do that. Well, why would that naturally happen? Because of that. That is the payout. That is the payout. When the ions come together and reach their sweet spot distance, that whole reason for all of this work. That's the reward. Now, do we see? Here's where we started. There's where we ended. Here's the enthalpy of the reaction. That's the lattice energy. Sydney and Megan, would you say that your cross country fall time, the highlight was the championships? Colton, would you say the highlight was, and then football team, the highlight was it? You know, what would you say is the highlight of like your hockey? Yeah. And what about you guys with swimming? So you do work, you go to practice, you wake up early, you go to practice, da 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 da. Well, the payout, yeah. So I don't know. That's a silly analogy. We come, we invest, we pay attention, we get stronger and stronger and smarter and smarter and smarter and smarter and smarter. Then we just kill all our other science courses from here on out. There we go. And that's the payout. So could I ask you to take a look at the very next page? Here, side by side, cesium fluoride and barium oxide. Holy smokes! Look at that lattice energy versus this. Still payout. Why is the lattice energy for barium oxide so much greater than the lattice energy for cesium fluoride? Go. So, all right. Lattice energy. Ionic bonding. Ionic bonding, lattice energy. Next, Coulomb's law. Those three things we have to just think about together. Okay? Dylan? Q1, Q2 over D. What advantage does barium oxide have over cesium fluoride in Coulomb's law? So the numerator for Coulomb's law will be 4 times that of cesium fluoride. Now, of course, the distance does play somewhat of a role, but we can see, oh, no wonder. Okay. Questions? All right. So, yes, we should watch the morning announcements, but otherwise, Lewis dot structures next. So if you have any final questions with lattice energy, please ask. So if we could find our way back, let's get to page 10. And here, could you please on your own read these couple of lines that begin with the star star? The more we learn about chemistry, the more gray that comes in. This isn't to like rattle our faith in what we've been learning. It's just to call to our attention that, science is our invention to best understand, explain the world around us. We're fallible, so everything isn't as black and white as I would like it to be. And so, like, talking about electronegativity, yeah, there's definitely bumps. We just apply where location is on the periodic table. This whole thing about lattice energy, we made that whole thing up to try to explain why things behave as they do. And there's evidence to back it, but we just need to keep that in mind. In fact, I think, we have our chem book. Well, if we included all the exceptions, it'd probably be triple in thickness. So, okay. All right. Lewis dot structures. So, I'm not sure how much we remember. I thought I would just kind of blitz through the very basics and then turn it over to you to jog your memory with some of these structures. We only truly do Lewis dot structures for covalent substances whenever you write a symbol of an element. So, for example, carbon. When we are constructing Lewis dot structures, just writing C represents the nuclei and all the inner core electrons. So, Damien, how many valence electrons does carbon have? You got it. Now, you don't have to, but the standard way is if we imagine there's a box around the element symbol, and then we begin placing them on the top, electrons by themselves first before we double them up. Up to you. Absolutely up to you. Now, Lewis dot. Can we please make dots? Not open circles, not stars, not triangles, dots. Dots are what we use to show valence electrons. Okay. Now, if you're like in the habit, that's okay. That's okay. I will definitely accept that, but I just want to encourage us to be using dots. Okay. So whenever a pair is being shared between two elements. So for example, if hydrogen is brought in with its one valence, well, hydrogen is an exception to Lewis dot. It only requires 2 total electrons to fill its valence shell. You know what? I am going to start. No, do we want to put, there's going to be exceptions and always. So I'm going to put like Lewis dot. Little things. Hints, I'm not sure, or like observations. Okay, so first thing is hydrogen, stable or low energy with a total of 2 valence electrons. So because of that, hydrogen will only form what we call single bonds. A single bond is a total of 2 electrons. And if this carbon is sharing with hydrogen, hydrogen is sharing this one with carbon, well, then we draw that as a line. A line means 2 electrons are being shared between the elements. And we definitely want to draw it between the element symbols. We wouldn't like have it outside. We're imagining kind of the center of each element symbol being the nucleus. And we'll learn that that's where the first pair will be shared, is between the plane of the nuclei. Okay, so it's stable 2, so then hydrogen will only create single bonds. Because of orbitals and sublevels, there is a restriction to how many pairs 2 elements can share between them, between the 2. We can have a single bond, that's 2 electrons. We can have a double bond, that's 2. And we can have a triple bond, that's 3. A single bond is longer than a double bond, which is longer than a triple bond. So as we share more pairs, actually the bond length decreases. But Grace, what do you think? But as we share more pairs, what happens with bond energy? Increase, decrease, stays the same. It does, yeah. To break 3 pairs that are being shared is greater than 2 than 1. Yeah. So bond length decreases, but bond energy increases. The goal is we move electrons around so that the octet is satisfied for our center element, So, for example, let's just do this first one together. Carbon, hydrogen, chlorine. We, in our kind of chemistry, build small molecules, not long chains, small molecules. So the first thing we have to decide when given a formula is what is our center atom that everything will be bonded to. Sometimes the formula easily reveals itself, like NH3, where you know nitrogen will be the center. There's only one of those. If hydrogen was the center, well, it can only form a single bond. It can only bond to one thing. How do we get 2 more hydrogens and nitrogen? But otherwise, so how do we decide carbon or chlorine? Your center element will be the element with the lowest electronegativity, furthest from fluorine. Except hydrogen, because it'll have the lower number of valence electrons, that will lead to the greatest opportunity of bonding, or the greatest number of bonds. All right, so I put carbon in my center. It has 4. It does not matter, Tyler, where we place all our other elements. As long as we can see everything, you can see and I can see everything. So usually, again, we go with the 4 sides. You don't have to. Where do you want to put your hydrogen, sir? You choose for us. All of them? All right. So I'll put this one here and this one here. Yeah, but for Lewis dot, as long as everything can be seen. Now, the only thing I would do is just move so it's more in the plane of the nuclei, if you will. But heck, yeah, you can do this. As long as everything can be seen. But I think, Tyler, what you were thinking is, oh, okay, if I'm going to have 4 sides around my center element, well, then I probably want to put my hydrogens on those sides. Everyone okay and where I'm getting the dots? And so I'm thinking we sort of remember. Okay, so we know hydrogen will single bond. You can keep going with this, totally fine. So carbon comes in with 4. Well, now through single bonding with hydrogen, carbon, if I pretend like the shared electrons all belong to carbon at the same time, well, then carbon has 1, 2, 3, 4, 5, 6, 7. 7. It needs 1 more. And each hydrogen, if I pretend like they're all on hydrogen, carbon, let's hydrogen take a turn for a second, then has 2, has 2, has 2. So chlorine, being a halogen, comes in with 7. And if it shares its 1, ding, 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 then carbon has 8, and then chlorine has 8. You could have put that here too. I think we tend to favor the way that we learned how to do Lewis dot structures. There's another approach where you could just come in and say, okay, I know carbon has 4 valence. Hydrogen brings 1 times 3, that'll be 3. Chlorine, 7. I know that carbon's going to be my center, so put hydrogens on that side, chlorine on that side, and then you just take 18 or 14 electrons and just place them around until the octets are satisfied for carbon and chlorine, and then hydrogens just have 2. If that makes sense to you, go for it. Go for it, go for it, go for it. So this would be our final structure, but it'd be fine to have that as long as everything can be seen, including paired electrons. You never, ever will have a lone electron that is not paired. If you do, you've done something wrong. There can be lone electrons in a structure. They're called free radicals. They're what we think triggers mutations in cells for cancer creation. But otherwise, no. So if you, for example, had this and had this lone electron, nope. In our structures. Okay, one more thing that we could say is an observation. Halogens, they all come in with 7. They all come in with 7. They only need 1 more for their octet. Halogens will only form single bonds. Now, they can form multiple single bonds, but they'll never double bond or triple bond. There's no capacity to do that. Okay, so could I ask us to go ahead and, yeah, why don't we go in order? So this will be the second one, the third, let me do 4th and 5th. Whenever you have more than 2 carbons, carbon will bond to the other carbon. So we won't, oh, I guess we could look at it. Oh, no, let's bond 1 carbon to another carbon. If there were 3, they would bond in a chain, if you will. And then you distribute the remaining elements symmetrically. So we have 2 hydrogens. We would put 1 hydrogen on each one. If you had 4, you'd put 2 on each. Okay, take it away. your choice of where you put your hydrogens, your lone pair, absolutely up to you, as long as everything can be seen. So we want to make sure that if you intend the dots to remain there, that you can clearly see that. We shouldn't have to question like, oh, was that erased and it's barely there? Also, if perchance while you're doing your structure, possibly you ended up with alone and alone, well, those will be paired. They do not travel on their own. So we need to show that. And it doesn't matter. You could have brought this to be paired with that one or this to be paired with that. It doesn't matter. Okay. And the main error that we make as we're making these structures is we neglect the pairs of electrons that are on bonded atoms. They are there and they're part of the structure. So we want to make sure that we're just keeping the lookout. Questions? Okay. Little bit of a twist. SO2. Okay, just keep an open mind. Dig in. I have a suggestion. It's just a suggestion. When you have more than one oxygen bonded to your center element, bond one oxygen at a time. So just look at one oxygen alone and then do the other. So Bryce, which one do you want to take care of? The one on the right, the one on the left? You choose. Sure. So comes in with 6. Sulfur has 6. So what are your thoughts, which were great, to complete the octet for oxygen? Yeah. Using, right, an electron of oxygen, an electron of sulfur. So there's a single, well, share another pair. And then the octet is good for oxygen, 2, 4, 6, 8. Well, it's also good for sulfur. Yeah, right? Before it even bonds with this, 2, 4, 6, 8. It's good. But this oxygen needs 2 more. What about this? So these are sulfurs. Right? 2, 4, 6. What if 2, 4, 6? What if oxygen keeps the 6 valence it brings, and then sulfur uses its electrons to form a bond? Octet satisfied, octet satisfied, octet satisfied. We call that a coordinate covalent bond. And that is where the electrons shared donated by one of the elements. Usually each element shares one to make the pair, but the electrons donated by one element, electron share donated by one element, versus each giving one. Now, two electrons shared or two electrons shared. So it's not that a coordinate covalent bond looks any different than any other single bond. Are we okay there? Okay. But as AP students, we need to be aware of this. Back to kind of the observations. Only carbon, nitrogen, oxygen, and fluorine obey the octet rule always. Only carbon, nitrogen, oxygen, fluorine. So what does that mean? Well, I just say, whoosh, thank goodness, when carbon, nitrogen, oxygen, and fluorine are there. Because I know I don't even have to consider that elements in the third period and beyond, in period 3 and beyond, can exceed the octet rule. It doesn't mean they do, they just are able to. So could then, let's see, so 1, 2, 3, 4, 5, 6. Oxygen came in with 1, 2, 3, 4, 5, 6. So could we, with this oxygen, do the same thing we did there? Double bond with one oxygen from sulfur and one oxygen from oxygen, or one electron from oxygen, and then bring those up. Oxygen never exceeds the octet, but sulfur does. We see. So how do we know which one? So I'm just gonna, do we see? Versus yeah. Sorry. How do we know what the preferred structure is? Easy peasy. It is called formal charge, a formal charge calculation. It is a formula that we have created that gives us insight into electron distribution. So we are going to choose the structure that has the electrons distributed best over the molecule. Okay. The equation for formal charge is the number of valence electrons that we would assign that element from the periodic table. Okay. Minus 1/2 the number of shared electrons minus the number of lone electrons. Okay, the number that we would assign from the periodic table, like the number of dots that we would place around that single element, minus 1/2 the number that are shared around that element, minus the lone number of electrons. In a structure, each element in your structure gets its own formal charge. We look at the formal charge set of values to decide which is the preferred structure. I promise this will make complete sense. Okay, so what this means is we are going to calculate a formal charge value for that oxygen, for that sulfur, and that oxygen. You could do them in any order, though, any order, because we're just looking at the values collectively. So the order that you place the formal charges doesn't have to mirror where they are, because I drew it like this. Maybe Isaac put the single bond above. All right. So for this first structure, I'm going to go ahead and calculate the formal charge value. Grace, you choose. Do you want the oxygen on the left? Do we want the sulfur in the middle? Or do you want the oxygen on the right? Sure. So I usually put a little subscript, and you can abbreviate formal charge as capital F, capital C, no problem. Or we could like draw that, okay, that's the oxygen that I'm doing the formal charge of. Now for sulfur, I don't have to draw an arrow because there's only one sulfur here. Okay. Number of valence electrons, Emily, that we would assign it from its position on the periodic table. What about for oxygen? What number? You got it. Minus 1/2. The way that we've drawn it, sulfur has 2, 4, 6 electrons that are being shared. Wait, what? I'm doing sulfur. Gerhardt. 2. So sorry. I was jumping the gun. Oxygen just is sharing 2 with sulfur. I'm sorry. Minus 1, 2, 3, 4, 5, 6. So it is a -1. The values that we hope for are 0. That's the goal. All right. So let's do the formal charge for sulfur. Sulfur is 6 minus 1/2. Sorry, this is what I was thinking of last time. 2, 4, 6 minus 2. It gets a formal charge of 1. Yes. I just want to respect the way inorganic chemists look at this equation. So at the end of the day, that would be okay. That would be okay if you just want to do number of bonds. I'm going to respect 1/2 minus the total number of shared, but that would be okay. And you don't have to write valence electron, you don't have to write the formula. All right, then the formal charge on this oxygen, 6 minus 1/2, 4 minus 4. Woo, there's our 0. It does not matter. It does not matter the order that you put your formal charge values. So Sean, do we want to put them -1, 1, 0, or do you want to put 1, 0, -1? You choose the order. Okay. We calculate formal charge values for each element, and then we compare the sets to each other. So in this structure, oh, look at this. this oxygen is bonded the same way that this is. So I only need to do one calculation for it. Oh, and look, this oxygen is bonded the same way that is. So I'm good. I know it's 0. But sulfur here is bonded differently. So 6 minus 1/2, 2, 4, 6, 8, minus 2. So this is the preferred structure. So structure 2 is preferred because the set of formal charge values are collectively closer to 0. So we're looking at all of them. Now, we want to be all 0s. That's ideal. But if it's an ion, we're not going to have all 0s because the formal charges will add up to give the charge of the ion if we're dealing with that. And we'll see that in a moment. So we want all 0s. A 1 and a -1 are both as bad. So it's not like a positive is better than a negative. So we would see a +1 and a -1, the same, like as far as 0 when we're evaluating. However, a 2 and a -2, it's almost as far as you remove from 0, it's almost exponentially worse. So a +2 and a -2, oh, that is wants to be avoided at all costs. So if we would have, for example, a 0, a 2, and a 0, let's just say, and then a 0, a 1, and a 1, this actually would be preferred because the 2, it's way worse than 2 1s. Just to answer that. Okay, so here, sulfur does go over the octet. Now, how do we know that we might need to do this? The wording of the problem will let us know. So if you're asked to do the Lewis dot structure of SO2, the wording will say more than one structure is possible. Calculate formal charge values to confirm which is the preferred structure. So the wording will let you know, be on the lookout. We can possibly create more than one structure. We decide which one is the correct one by formal charge values. All right. Can we do one more? I know we can. I know we can. Okay. Damien, can you share something you've learned today that you didn't know before today? Yeah. Of course. I'll kind of plant a seed of why. Why can elements 3rd period and below? So not 2nd period or 1st period. Why 3rd period and below? Just something to think on. Okay, nitrate. Can you get the structure? Well, first thing that I see is it is charged. So here is my suggestion. This is page 14. My suggestion is nitrogen's our center. I would assign nitrogen 5 valence from its position on the periodic table. Before I add the other elements, start to bond, I'm going to take care of the charge on the center element. You don't have to. I suggest that we do. That will get us most efficiently to the correct answer. Most efficiently, so with the least amount of hiccups. So I'm going to assign it 6. Doesn't matter where we put our oxygens. But if we have more than one oxygen, I suggest bonding one oxygen at a time. I chose to do the right one first. Totally doesn't matter. So each comes in with 6. I'm going to double bond. I chose the one on the right with that oxygen. But each of the other oxygen needs 2 more. And nitrogen and oxygen never, ever, ever exceed the octet. That's out. So coordinate covalent bonds. So our 2 oxygens that are singly bonded have 3 pairs of electrons, but then we have 1 double bonded oxygen that has 2 pairs. But we have an extra electron in this structure beyond being neutral. Anything that is charged in a Lewis dot structure must be placed in brackets with the charge as an exponent. I chose my double bond here. Sydney, did you put the double bond on the right oxygen? Great. Dylan, did you put the double bond on the right? Did anybody choose the bottom one? Or did you put it on top, on the left? Well, this is going to be an aqueous ion, but it's going to be flipping around if we have it dissolved. And so who's to say that this is the one that should be double bonded, or this one, or that one? Kind of what makes that oxygen more special than that one or that one? Because this oxygen, it is winning because it has a double bond. It's going to have a shorter bond length and a greater bond energy, which means it is lower in its energy. Well, again, what makes that oxygen more special than this, When we measure the length of these bonds, which we can measure because we can tell where nuclei are, all of those bonds are the same length. And they are not as short as a double or as long as a single. They're all the same, but they're longer than a double, but yet shorter than a single. So the idea that we propose is actually this double bond takes a turn on each oxygen. And it's alternating so fast that when we measure it, they're all the same. And, well, so the very next moment, the double bond is here, imagine. And then the very next moment, it's on the left oxygen. It's switching so quickly that we say all of these are correct. That the double bond resonates between all of them. That's where we will pick up tomorrow. Enjoy your Monday. One more day.